Hello, everybody. Welcome to our webinar, Scientific Augmentation in the Classroom. My name is Tanya Siemens, and I'm at STEM Central. It's a website and community practice for broadening participation in STEM education. And I'm joined here with Dr. Jonathon Grooms, Dr. Hector Torres, and Vivek Karki, and we will be presenting the webinar today for you. I just wanted to share a little bit of housekeeping. This is about a 1-hour webinar, and we're going to have about 30 to 40 minutes of presentation, followed by discussion through the questions feature. If you have a question, feel free to type it into the questions box, and we'll get back to you with answers as soon as we can. There are some places where we pause during the presentation to allow you to ask questions. We're going to start out with an introduction from Hector Torres, who will introduce the program and our speakers. So, Hector Torres.
Good afternoon. Happy to have you all as part of this exciting opportunity to learn about argumentation or argument-driven inquiry as well as socioscientific issues. I wanted to thank Tanya for helping us put in this webinar together, and of course Dr. Grooms, who's going to be our first person that is going to do our first seminar, webinar on this project. So that you know what we are doing, this is a broad participation research project, and it is intended to expand the scientific literacy at Bethune-Cookman University. What we are trying to do is to, by the way, the project is entitled Investigating the Effect of Socioscientific Argumentation Development on Student Academic Success. And it is to investigate how to produce science, technology, engineering, and mathematics or STEM graduate with argumentation expertise. One of the things that we are beginning to see is that most of our students do have the content knowledge, but being able to use that content knowledge into ill-structured problems that require scientific or evidence-based reasoning to inform decision is sometimes troublesome. So we're trying to identify and give students the opportunity to engage in dialogue, discussions, debate, and argumentation. And for that, we have two outstanding experts in this area. One is Dr. Jonathon Grooms. He's a professor at George Washington University. He is part of our team as a consultant. And Dr. Groom brings a lot of expertise in the area of argumentation. With us, we also have Vivek Karki, who is our research assistant. And we are going to try to make it as exciting as we can. If you do have any questions, please feel free to ask. We're going to try to answer as many as we can. This is going to be recorded, so you can actually go back and see it one more time. So without further ado, let me introduce to you Dr. Jonathon Grooms.
All right. Thank you, Hector. I really appreciate that introduction and an overview of the project. Looking forward to sharing some ideas with everybody today and getting your questions and feedback and trying to make this as much of a discussion as we can in this format. So today we're going to focus, as Hector mentioned, on kind of the scientific argumentation aspects of this project and some different ways that we're thinking about engaging students in argumentation and things that you can do in the classroom to really foster that scientific practice. So just a little bit of an overview of things that we'll chat about this afternoon. Just a quick kind of intro and overview of the importance of scientific argumentation, why we even care about it. I imagine many of you are science educators, scientists that are joining us today, so that should be familiar to most of us, I imagine. And then there's a few instructional models that I've been involved with in terms of developing and things that we're hoping to work into the project in a variety of ways. So we're going to kind of have an overview of those and gives you a chance to see what those look like and how they could function in the classroom. I didn't want to structure this so much as a research presentation, but I do want to share just a couple of pieces of data just kind of in support of the instructional models that we'll chat about. So I've got a few slides on that. And then, of course, just want to point you toward some additional resources so that you can potentially take some of these ideas and use them in your own classrooms, your own research, and that sort of thing. So if we dive in and think about what is scientific argumentation, you can kind of take a second to think about that we think of argumentation a lot of times as being this combative, potentially angry kind of scenario or engagement with another person. And of course, in a science classroom, that's not the kind of argumentation that we're going for. So scientific argumentation is what we call or think about as a process of proposing and supporting, critiquing and refining claims, right? And those that process is really embedded and supported by the criteria that are valued in science. So I had the opportunity just the other day, I was down in Atlanta, Georgia, the home of Coca-Cola. And so we were trying to kind of make sense of this. And you could imagine that you could have an argument of what's a better product, Coca-Cola or Pepsi. And you could generate lots of different arguments supporting your stance in that particular arena. And you could even generate tables and graphs and some very empirical evidence to support that one company or one product is maybe better than the other. And even though you're generating a rigorous evidence-based argument, we wouldn't consider that a scientific argument because we're not relying on those theories, laws, and models and things that are really valued within the scientific community. So it doesn't mean that scientific argumentation is the only type of rigorous argumentation, but it is specific to our field and the domain that we're working in. And so other reasons why this is important for us to think about and why it's important for our students to engage in this is simply that it's a core epistemic practice of the scientific community, and it makes science different from other ways of knowing. So in history or analyzing literature and things of that sort, we generate arguments in those contexts as well, but we don't have the same criteria there as we do in science. So it's something that is unique to our field. And it also provides a venue for the social construction of scientific ideas. So that's within the broader scientific community as we're trying to kind of build and further our knowledge base, but then also within the science classroom for students to interact and engage with each other to build their understanding of the current science that we're trying to teach them. And it engages students in the practice of science, kind of writ large, so to speak, that this is what scientists do. They generate these knowledge claims. They're critiqued and evaluated by the community and revised and refined over time. So if we have our students doing that same thing, then we're helping bring them into the scientific community in that sort of way. And as Hector mentioned, one of the goals of this project is to help students kind of develop their scientific literacy. So if we can help students to understand what it means to argue and think scientifically, and then hopefully apply some of that thinking to relevant aspects of their personal life or issues kind of outside of the science classroom, right, then we're helping them to bring that science into meaningful consideration in other contexts. And if we borrow a little bit, so the project with Hector and Bethune-Cookman University is obviously looking at undergraduate students, but if we borrow a little bit from the K-12 literature and the new framework for science education, we really see that this idea of arguing, critiquing, and analyzing is really central to the scientific process, and and kind of serves as this go-between, or this method for moving between the investigative side of science and then the more kind of developing explanations, solutions, what some people may kind of think of as the maybe more engineering or practical side of science. So that argumentation, that process allows us to move efficiently between those two areas. So that's another reason why it's important for us to think about and focus on with our students. So when I think of a scientific argument and the work that my colleagues and I have been doing, our scientific arguments that we work on with students have three parts, three main pieces being the claim, the evidence, and then the justification of the evidence. And of course, there are a few different frameworks. Probably one of the most well-known frameworks is the claim, evidence, and reasoning framework with McNeil and Krajcek and that research group. Very, very similar. There are some small differences in wording and kind of the ways that we think about the three pieces, but our group and McNeil group and Krajcek and folks, we all get along and think about this stuff in very similar sorts of ways. So as we move through this, anytime I refer to a scientific argument, these are the pieces that we're looking for. In our work, you can imagine the justification of the evidence is by far the hardest thing for students to get a handle on, and that's across the board at all different grade levels. So coming up with claims is a reasonably straightforward process for students to get a handle on, as well as evidence. That's not as hard as some might think. So if students are generating their own data, they can use those data and figure out the most important pieces to apply in order to generate an answer to a particular question. But then that justification piece, where we're asking students to really identify the scientific ideas, theories, laws, models, those sorts of things that help support and frame their investigation and their argument as a whole, that starts to get a little bit more difficult. But I do think that's one of the more important pieces, right? We want students to understand how their ideas fit within the broader context of what we know and how we use that body of knowledge. So that's somewhere that we always have to push our students a little bit to make sure they're making progress there. All right, so ways to support students in developing arguments. So kind of leading into these different instructional models that we're going to talk about. If we have these different models in place, right, that's a support for us as teachers, as instructors of various courses. It gives a bit of a format for us to think about how an activity can be structured so that students have those opportunities to engage with each other and engage with data and evidence in meaningful ways. Another thing to think about is that as we do various activities, we want to make sure that the activity itself is authentic and educative for the students. And what I mean by that, authentic in the sense, maybe the most simple sense, that students don't know the answer going into the investigation. Oftentimes, so my background is in chemistry and physics education, so often I've seen teachers, and I've been I could be accused of having done this as well in the past, that we go into an activity and we're asking students to generate Newton's second law or something like that. So, you know, a quick F equals ma type investigation. And we've just spent the entire last week of our course kind of proving to students, so to speak, that indeed Newton's second law is F equals ma, and then we do the investigation. So that's in no way authentic, because students are already aware of what the outcome is supposed to be and what they're trying to figure out. And there's really no feedback that they're going to get during that investigation that is going to help them kind of move forward in their thinking. And then it's important, and maybe goes without saying, but I like to be explicit about it, that students need to engage with the ideas of their peers. If they're generating arguments and ideas within their group, that's great. That's a good first step. But if they're not kind of critiquing and evaluating the ideas of individual peers and groups of peers, then they're really missing out on that opportunity to engage in the argumentative practice. So if we think about the first instructional model here, argument-driven inquiry, there's a couple of things that we're trying to accomplish with the model. So of course, as the name implies, so we're placing a greater emphasis on the role of argumentation and argument within science. So we're making students really aware that this is a practice that they should be doing, and it's an important aspect of science. And not only are they engaging in argumentation, but they're engaging in a variety of scientific practices that are valued in the scientific community. So they're designing investigations, they're collecting and analyzing data, they're communicating the information. So there's a variety of things that they're doing that scientists also do. So we want to make sure that we're modeling all of those different practices. Excuse me. And of course, as the instructional model is structured, we're providing students with scaffolding to make sure that they're successful throughout the process, and then providing feedback at various points during the instructional model so that they can actually improve and figure out how to get better at these practices. If we don't provide that feedback, then we're missing out on the mechanism there for the students to actually get better at these things. So the ADI instructional model has 8 stages. It's a little bit more rigorous than perhaps a typical lab investigation that you might be familiar with for a high school or an undergraduate kind of setting. So I'm going to move quickly through the 8 stages just to give you a bit of an overview, and then I'll go into a little bit more depth with each of them. All right, so stage 1 is simply introducing the task, the topic of the investigation, and the research question. So each lab has a question that the students are going to be able to answer by the end of the investigation, and the argument that their group comes up with is a direct answer or response to that research question. Stage 2. The groups are going to actually develop and implement a method to collect data. So they have to come up with their own plan. So we're not giving them any sort of step-by-step procedures or anything of that sort. We do give them some kind of hints and some guiding thoughts and ideas so that they're not going astray and doing something that's going to be unproductive. But the goal is for them to figure out the method, implement that method, and generate the data that they need. Then stage 3, each group is going to develop a tentative argument. So again, we have that claim, evidence, and their justification, and that argument is a direct answer to the research question. Stage 4, students participate in what we call an argumentation session. I interchangeably refer to the argumentation session as the whiteboard session, the round robin session, the gallery walk. There's lots of different terms that folks use depending on the audience that they're working with. But essentially all the groups are kind of moving around the classroom to critique and evaluate and provide feedback to their peers about the arguments that have been generated. And stage 5, this is an opportunity for the teacher to become a little bit more front and center, but only so much so as that the teacher is leading an explicit and reflective discussion to make sure that the science content that is supposed to be the focus of the investigation is getting out there. It's front and center in the classroom so that the teacher is ensuring that the learning goals are being met, but doing so through a discussion format, not a, now the teacher comes in and gives the right answer and launches into this kind of direct instruction PowerPoint kind of approach. That's not what we're going for. Stage 6, each student then writes an individual investigation report. I'll talk a little bit more about that, but it's a bit more of an essay format, so not a typical kind of lab report format that you may be familiar with. Stage 7, those individual reports come in. They're actually blinded, so no one knows who's written that report. They're given to the instructor. They get kind of shuffled around a little bit and redistributed to the students, and they undergo a double-blind peer review process. And then finally, stage 8, after that peer review, the written reports go back to their author, and the author revises the report based on the feedback of their peers, and then those reports, revised reports, get turned into the instructor as kind of the final piece of an individual ADI investigation. Right, so other kind of reform or inquiry-oriented instruction that you may be familiar with incorporates some of these ideas. So ADI is not an entirely new thing. I don't want to try and make that impression. So often students are answering a question, and we can have them develop methods on their own, and we do have them write reports. But often those reports, once they're written, go directly to the instructor, and the instructor is the only person that provides feedback or actually even reads the report. And then oftentimes that explicit discussion may come at the very end, or as I mentioned previously, it may be the very first thing. We may discuss the content right off the bat before students launch into the investigation. Right, so ADI is really, as I mentioned, putting that focus back on argument and argumentation by bringing in some of these other aspects and other components of the instructional model. Right, I feel like I've been talking a good bit.
Sorry. Hello, this is Tanya. I just wanted to jump in that we have a question from Nancy Morvillo.
Yeah.
How long do these labs last, and what is the time frame?
Yeah, that's a great question. I think that was Nancy. So great question, Nancy. The time frame really varies depending on kind of the grade level and group of students that you're working with. So I can say for like a high school kind of classroom, if you're working with a 50-minute class period, depending on how many of these investigations you've done, if your students have gotten kind of good at it, 3 to 4 class periods, maybe 5 if it's a really kind of rigorous data collection lab. In terms of undergraduates, in like a typical kind of 3-hour lab block, the way that folks have worked with that, it's a bit odd. It works out to about like 1.5 of those sessions, but they tend to be broken up. So they'll do part of the 8 stages during one session. They'll finish up, they'll have their data, they'll do the whiteboards and the argumentation session, and then typically write the investigation report as a homework activity, bring that in the following week, and then the first half of that next session is devoted to the peer review process. And then the second half of that lab session will be devoted to moving on to a new investigation that may be an ADI investigation. It may be a shorter kind of technique or equipment related investigation to set the stage for an ADI that may happen the next week. So work that colleagues have done in undergraduate contexts, 5 to 6 of these investigations is typical within a semester as compared to doing a unique investigation each of the 12 weeks or so that may be in a college semester. Great question. Right, so.
Just a follow-up question, yeah, sure. Dr. Torres here. So it's a two-part question in a sense, and it has to do with curriculum and instruction. So what is it that I need to do within my curriculum? Do I need to change my curriculum to make sure that I introduce this task and guiding questions? That's the first question. And the second question is about instruction. So now you're asking me to not be in front of a student and tell them what to do, what not to do, and believe me, and all that. but to ask them to do their own learning and their own teaching, and I'll be the guiding piece of it. Is that what you're saying, or?
That's exactly what I'm saying. So answering the second part of that first, this kind of instruction does require a bit of a shift in mindset and kind of role of the instructor. So in this case, the instructor kind of introduces the activity and gets students focused on the task at hand, but then a lot of the thinking and reflection and learning is taking place in the small groups and between the groups as they engage in this argumentative practice. The teacher is more explicitly involved in that stage 5 discussion, but you're right, this requires a shift in thinking that the teacher is not kind of the holder of all knowledge within the classroom, that the students are responsible for putting a lot of the pieces together with the assistance and the guidance of the instructor. Absolutely, the instructor is not completely hands-off. And then as far as the curriculum goes, there are choices, right? If you're going to teach this way, and as I've described, it does take a bit more time than maybe a typical investigation, then you have to make some decisions of, maybe this topic doesn't need as much emphasis as I tend to give it, or maybe I don't need to teach this other idea at all, that it doesn't fit any longer. So you have to kind of reshuffle and rethink things, and maybe reserve ADI for those high leverage topics that you really want students to dig into, and not so much just the everyday passing kind of topic or idea that you may mention within a course. Right, so I'm going to keep on moving along here to make sure that we have time to get through the models and really get moving here. So stage 1, as I mentioned, the instructor is introducing the task and the guiding question. I've got a sample here of what the first page of the handout looks like that students will use. So it's a bit of reading there in the beginning to kind of get them focused and thinking about the science content that is involved. This particular activity comes from a biology resource book that we've worked on. So this is a high school level investigation, if you're wondering. Excuse me. And you'll notice perhaps right off the bat that there are no instructions. As I mentioned, there's no procedures that are written out here for the students to follow. They're given a task that finishes up with the guiding question at the very bottom of that page. And then students have some things to think about, which will be on another page accompanying this. And then they start to design their investigation once they're kind of oriented to the task and the problem that they're investigating. Excuse me. Stage 2, the students are designing a method and collecting data, as I mentioned. So they have that question. They need to figure out what data are important, what's going to allow them to generate a claim that responds to that question, how many trials do they need, those sorts of things. How are they going to actually analyze their data once they generate it? Some things that we've done to help students through that process. We've generated what we call investigation proposals, a variety of these proposals that help students kind of think through this idea of making a hypothesis, generating a procedure that's going to result in data that they can use to help answer that question. We ask them to kind of think through how they're going to analyze the particular data they collect, what do they predict is going to happen. And if you kind of follow through the handout, there's this general if and then kind of format, kind of along the lines of hypothesis testing, kind of hypothetical deductive reasoning, those sorts of things. So this is a useful way that we've helped students kind of get into this, and perhaps once they've done a couple investigations, you don't need to use this as a scaffold anymore. And just kind of noting that not all investigations in science are hypothesis driven. There can be very observational kinds of investigations that we do. So we have a different format as well to kind of work students through that process in terms of thinking through that sort of investigation. Then moving to stage 3, as I mentioned, so stage 3 is going to be developing that initial argument. So each group is going to analyze the data that they have, and they're going to craft this argument that coordinates their claim, their evidence, and their justification. And you can see this is a group of high school students, but they're all working on the whiteboard to try and put things together to make sure that they've got all of their pieces covered. The young man is drawing what looks like a dinosaur. I'm not sure if that's actually what that is. This was a biology class. They were looking at like evolutionary relationships. So that, I don't think that's a doodle. I do think that that's actually relevant there, what they're doing. And you may notice the justification that these students are writing is quite a robust set of ideas that they're trying to flesh out of how they're making sense of this particular investigation. All right, so I want you to maybe play along here with me and kind of think through how you might do this and what this could look like. All right, so if we think of another activity that we could have students do, and this is just a simple one, I think that's accessible in this format. So we ask students how wrapping a wire around a nail is going to influence the strength of an electromagnet. So if you make a simple magnet, electromagnet with a battery, a piece of wire, and a nail. And I'm not sure, let's see if, I thought maybe that I could point to that. So if we're varying the number of coils that are wrapped around this nail here, I'm not sure if you can see my pointer as I'm moving it along, but we could get some different results that happen in terms of the strength of that electromagnet. If we think about some sample data that students might generate, so if they vary the number of turns from 5 to 25, they do a few different trials, and more often than not in this investigation, students are trying to pick up paper clips and simply counting the number of paper clips and generating a claim based on about strength, rather, based on the number of paper clips that they're able to pick up. And so the more paper clips you pick up, the stronger the magnet. So if those are the data that we're working with, a sample argument that might result from that could look something like this. Right, so the student's generating a claim that increasing the number of turns increases the strength of the electromagnet. They've provided their evidence there. Right, so we don't have the data table any longer. They've taken that data, they've analyzed it and interpreted it through this graph. And they've provided a statement there that helps us understand the relationship between those variables. Right. Well, I'll also see that they have not labeled the x-axis there. That's something to potentially critique. And then if we look at the justification, right, they're really identifying, and they've used bullet points in this case, and that's fine, in my opinion, on the board when it comes time to writing. This would probably be a little bit more fleshed out, but just really hitting on the key ideas that help them understand why this relationship is the way that it is. And they've included the final bullet there to help us understand why this idea of more paper clips equals a stronger magnet. Right? We need more force to pick up more mass. So they're bringing in some other understandings about forces as well.
Dr. Grooms, I wonder if we can pause for a second and ask a few of the questions that have
Sure.
accumulated in our question box here.
Great.
Okay, the first one is from Akinyala Abdullah. I hope I said that correctly. The question is, on average, how long are the student reports and how many students are in a group, say, in a class of 25?
Good question. So we require that it's weird to say it this way, we do not allow the reports to be longer than 2 pages. So we find that if it's longer than that, students are really starting to repeat themselves or bring in information that's not relevant just because they're simply trying to fill up the required space. So we limit it to 2 pages, and if they write less than that, that's fine, as long as they're hitting the key points, and we'll talk about that in the upcoming stages. And then numbers of groups, we we like the idea of 3 in a group. I realize that that's not always possible depending on class size and the equipment that you have available. So most teachers that we work with tend to push those groups up to 4. I would really urge you not to go over 4, that it starts to get a little bit onerous if you have more than that in a group.
And how do you form the groups?
So that there are a variety of ways you can do that. Teachers that we've worked with will have mixed ability groups based on some sort of kind of external measure. They may just know that this particular individual is a strong writer or a strong speaker, and another student in their class is a little bit more shy. So perhaps they'll put those individuals in the same group so that they can kind of work and learn from each other. One just kind of general rule of thumb that I like to use anytime I'm forming groups in order to kind of make sure that we're being equitable and doing things kind of justly from that perspective. If an individual is a minority in the classroom or within the science community, then I do my best to make sure that person is also not a minority within their smaller group, their lab group that they're working in, right? So it's just a means to make sure that we're giving everyone an opportunity to kind of contribute and make sure that they're able to be a contributor within that group.
That's great. There's a lot of questions about the groups here, so I'll just jump to the next one from Claudette McFadden. She asked the size of the groups, and you already answered that. So, and then she also asks, what does the rotating from group to group look like? Are they timed? Like, how does that work?
Sure, that's a great question. The timing is really up to you as an instructor. I would definitely initially encourage kind of having a general time in mind. You don't necessarily have to have a timer per se, but with younger students, if you give them too much time, then the conversation quickly turns away from the science and to more kind of personally relevant conversations or topics. So giving them 3 to 5 minutes is a pretty good rule of thumb that they can ask and answer some good questions in that time without getting off task. And then there's no need for every group to rotate to every other group. If you have 8 or 9 groups of students in a class, if you move around from whiteboard to whiteboard, after 2, 3, maybe even 4 other presentations, you're going to start to see some of the same ideas, and the interest will fall off a little bit at that point. So I would keep it to 2, maybe 3 groups and make sure that you kind of keep that moving efficiently.
That's great. Let's see. One other question that we had here is regarding the materials, and Dorothy Silverman would like to know if any of the handouts that you've been showing might be available for people to borrow or adapt.
Sure,
I'll put them on STEM Central.
Yeah, I'll point you to some resources. I actually have a slide at the end with some additional resources, some websites where you can go and get things as well. Yep.
Okay, great. I'm going to do one more question, and then I'm going to hold the rest of them until a little later. Oh, like you're already on your question slide. That's great.
I skipped over another sample. Yep.
Okay, so this is related also to this group activity, and it's Carlietta Paige Anderson. Is the content of the reports limited to the handout, or is there an expectation to identify external literature sources to add more support or justification to the claim?
Wow, that's a fantastic question. I would of course want students to bring in as much as they can to help kind of make sense of an activity or investigation. We do not require it just because I would say mainly a time reason. If there's time and students have access and the resources to do that additional research, then I think that's a great thing to add. Any of the activities that we write and that we've done in our research and classroom settings, we'd provide enough information in that initial handout that they can justify their argument and their claims with that information alone. But of course, if they can bring in additional sources, that's just going to make it an even stronger and kind of richer experience.
Okay, great, thank you. I'll just pause the questioning for now, and you can move forward, and we'll hold the next group of questions for a few minutes. Do you have another question slide coming up, and I can just wait for that one to
Yes, yeah, at the
okay.
end of the 8, so we have like 3-4 more stages, and then we'll have some questions.
Okay,
sure.
great.
All right. So stage 4, some folks have kind of already asked about this. So this is just a class shot of what that looks like. So you can see all the different groups have their whiteboards propped up, and individuals will move around from board to board. So if you look here in the foreground, the gentleman in the white shirt with his foot up on the chair there. So his group would have created the whiteboard that's closest to him. And then the 3 individuals that are nearby jotting ideas down in their notebooks, they would have created a different argument on one of the other whiteboards in the room. And so they've kind of rotated around. They're asking questions and making note of this gentleman and his group's argument so that they can critique and kind of evaluate the work that's going on. So again, these students would rotate to 2, maybe 3 of these whiteboards within this session. So it doesn't necessarily have to be an entire class period. That just kind of depends on how many boards you want students to move through. Okay, so stage 5, this explicit reflective discussion, as I mentioned, the teacher's leading a discussion about the core ideas of the lab, the quality of the investigations, what things were scientific, what things maybe were less scientific about what they did, bringing in cross-cutting concepts, nature of science ideas, really using those whiteboards and those arguments to frame this whole class discussion of what ideas did we see, what ideas do we think are better supported than others, and making sure that the science is really being discussed as part of this investigation. And then stage 6, this is a screenshot from the handout that the students would receive, and it's on all the handouts, so it's a common set of text that we use. And when we ask them to write the report, as I mentioned, it's 2 pages or less. We do ask that it's typed, just it makes it easier to have multiple copies, and frankly, for reading purposes during the peer review and the final draft. We ask the students to answer 3 main questions. This turns into 3 sections of the report. So what question were you trying to answer and why? So that's kind of an introductory paragraph. What did you do during your investigation, and why did you conduct your investigation in that way? So that's their methods section, but we're not looking for a step 1, we did this, step 2, this, step 3, this other thing. We ask them to write that in a paragraph form that's more descriptive and explanatory than simply a listed, numbered, or bulleted procedure. And then the 3rd section is, what is your argument? That is essentially taking the whiteboard that they've generated, that they've refined based on the feedback of their peers, and turning those 3 sections, the claim, the evidence, and the justification, into a paragraph and linking those all together. And then stage 7, this double-blind peer review process. So you'll see this group of students here in the foreground again. Each of those students in the group, and this is the same lab group they've been working in, has a copy of a report sitting in front of them. So that report is from one of their classmates. So they're all reading the same report. They're all providing feedback and critiquing it based on the rubric that the young lady in the top right of the group, she's filling out the rubric based on their critique and evaluation of this one report. So once this report is reviewed, then it would go back to the teacher, and that report is done. It doesn't get distributed to another group in the classroom. So we just get the one review from the group, and then we use that for feedback purposes. And this is just a kind of zoomed in shot here of the peer review guide. So there are several criteria that are there that students are looking for, and the reviewers, the peers, are simply indicating that no, this idea is not present in this particular section, it's partially there, or yes, it's there, I can identify it very clearly. And then we ask students to provide feedback and kind of critique and comments if they mark anything no or partially. Right, so it's not enough to say that something's not here or add more. We need to actually give feedback that's going to be useful in terms of making that report better. And then you'll notice there's an instructor place on this rubric as well. So the instructor can use the same exact rubric to score the report, and you have the initial comments right there next to the report, the rough draft and the final draft, and you can kind of put it all together and give some sort of score if as the instructor you need to have accountability and grades. It could serve that purpose. Right, it's kind of a zoomed in bit of the peer review guide. Again, making sure that the reviewers provide specific feedback if they mark a no or a partially. That's the only way that the original author is going to be able to bump that up to a yes, is by getting that feedback. And then we give a space for the author to actually comment that, you know, these are the revisions I made, these are what I did to make this report better, and address these comments. And then stage 8 is revising that report based on the student feedback, and then submitting it to the teacher for kind of a final evaluation. All right, so any questions on those stages?
Yes, there are some questions. I wanted to also, before we jump into the questions, just note that it's 15 minutes left of the webinar, so we're going to try to wrap this up at 3. We have a question from Claudette McFadden. In the example of an argument, the justification sounds like evidence that supports the claim. Will you say more about the difference between evidence and justification?
Oh, that is definitely a tricky thing to tease apart. So in the work that we do, evidence is data that has been analyzed to show some sort of trend or pattern or a relationship. And then we ask the students to have an explicit interpretation of that evidence. So again, if we go back to the graph from that electromagnetic activity or electromagnet activity, we can see that the students have analyzed that raw data by taking some averages and plotting the relationship between number of turns in the electromagnet and the strength based on number of paper clips that it picked up. And then they provided an interpretation of what that relationship means. As we add more turns, the magnet gets stronger, as evidenced by this increasing direct kind of relationship that they've noticed. So that's what we would consider evidence. As far as the justification, that's where we're looking for those science ideas to come into the conversation.
Okay, thank you. And we have more questions piling up, but I also wanted to make an option available to people. If you'd like to try, if you know that you're on a computer that generally works really well in terms of your microphone and speakers, we can unmute you and you can ask your question out loud. So if that's how you like to ask your question, you can click that little raise your hand icon and I will unmute you. So it's your choice to type it in, or if you prefer to ask out loud, that's an option. So you just click the little hand raise icon. And so the next question is from, that was typed in, is Catherine Olson asks, can argumentation process be done as efficiently in a non-lab setting, such as a class period or a review session held by a teaching assistant or learning assistant?
That's a great question, and I think it can. It's just the nature of the argumentation that's happening is going to be a bit different. So in that context, right, students are likely not to be generating data. But if I maybe skip ahead a little bit. So here's an example, and I can go back, but I'm just using this to answer the question. If students are provided some data or a data table, right, you can have them still engage in this argumentative activity. What do these data mean? What kind of conclusions can we draw? And have them engage with each other's ideas. You're still going to be fostering that argumentative practice, which is really key to their learning. So there doesn't always have to be this data collection and kind of laboratory component to it. There are other ways to get around that.
Okay, and there's 2 more questions in the queue. Thank you for that. And And I know you have a few more slides, so we're going to go ahead and do these 2 more questions, and then hopefully you have time to finish your slides and leave some room for a few more questions at the end. I want to be cognizant of the time with 10 minutes to go.
Sure.
So another question is from Gren-Marie Agrazar. How many reports does each group grade?
So the quick answer is they will grade the same number of reports as there are students in their group. Okay, so if everybody brings in a report, then they should be evenly distributed again. And if there's 3 in a group, then they'll grade or review 3 papers in that class period, and then that should account for all of the reports.
Great. And the next question is related to that from Nancy Morvillo. Apologize for that mispronunciation. How well does the peer review process work? In my limited tries, students are often too lenient or too harsh. The student that is evaluated is often upset with a bad evaluation, quote, bad evaluation.
Sure. So that's a tricky thing to navigate, and it kind of centers on classroom norms, right? So we have to set the stage that this is a process to help make us better. So that's one thing to get across. And if you're getting feedback, the feedback is to make your report stronger, not to indicate that you as an individual are deficient in some sort of way. So making sure we have that emphasis is super critical, and making sure that we actually model and work with students to help them provide constructive feedback. So maybe at the very beginning of this peer review process, you grab a random report from a different class period, a different lab section or something, and use that as an example and go through as a class. Like, okay, let's read this introductory section rather, and use the rubric. What kind of feedback would we provide this author? And then the instructor can model the kinds of feedback that you would want to see students giving. And if you notice that student that's being a bit harsh, or perhaps making it more of a personal kind of endeavor as opposed to a scientific process, then you can address that to the whole class and make sure that they understand, what the actual purpose and intention is. And I can actually show you. I have a graph if we get to it. If not, I can share it with you personally, individually, to show kind of how the rough draft and the final draft changes over time, and it's actually quite dramatic.
Okay, thank you. I'm gonna pause the questioning for now, so feel free to move forward with your presentation.
Sure, and I'm going to move pretty quickly. So these next 2 instructional models, generate an argument and evaluate alternatives, are very much related to ADI. I started with ADI because it's the bigger piece, right? There's more stages, there are more things going on. Kind of like the question just asked a moment ago about a review session. This generate an argument instructional model, you can see the 4 stages there. It simplifies and kind of changes the process in that students are not collecting data themselves. They still do many of the same pieces. So it's not an entirely different endeavor, right? And just to skip to what this could look like. So this is an activity you might do with some middle school students. This isn't an undergraduate kind of activity, I wouldn't think. But something like the solar system, our students would have a very hard time collecting some of this data. And granted, they could look it up on the web, just like we did to generate the data table here, but we can provide students with a set of data and still give them a question. In this case, how many planets are there in the solar system? And have the students come up with a set of rules and criteria to determine which of these objects in the data table should be considered planets. And it's often interesting. Sometimes they'll come up with a number that's not in agreement with kind of what science has said that they're are in terms of planets. Sometimes they'll come up with more or less, but it really generates this rich discussion of how we analyze data and how we make sense of this. And they would still generate the argument on the whiteboard and do that argumentation session as well. In this case, the writing could be a little different. Maybe they just write an argument paragraph because they don't necessarily have this really rich discussion to contribute related to their methods or procedures, because it's all built into the analysis portion of things. Another benefit of this big kind of complex topics, again, that students would be hard pressed to generate their own data on, we can provide them different types of data, maybe satellite images or graphs that have been graphs of data that have been collected over long periods of time, right? So we can use these pieces of information, pieces of data for them to still engage in this process and generate arguments. So again, it doesn't always have to involve this explicit data collection piece. And just a third example, so looking at something like evolution or natural selection, those sorts of things, which again happen over broad time frames that we can't necessarily investigate efficiently in a classroom kind of setting. We provide some background, some sample data, and then we give them some ideas that they want to probably use to help guide their understanding, their analysis of that data can be helpful. Right, I have a question slide coming up, but I'm going to skip that if that's okay, and just jump to the evaluate alternatives. This one, again, is just a slight twist on the ADI model and the generate an argument model, and that in this case, students are given a couple of potential explanations to begin with. Right, so there's an interesting phenomena, and students can generate data in this case, or they could be provided data, and then have to try and figure out what explanation is best supported by the data that they collect. Right, and this particular model really has a focus on counter arguments as well. So looking at one example here, placing ice on ice melting blocks, you get different rates of melting. It's a very interesting phenomenon based on heat transfer and conduction. And there are some interesting misconceptions, alternative conceptions that students have related to this idea. And we use those to actually form the basis of 3 different explanations. So then students could generate some temperature data about what's going on with these different blocks, and then figure out, well, I think explanation 1 is best supported by the data that I've collected. And then their argument would be in favor of the explanation they've chosen, and then they would provide counter arguments for the other explanations. So it's just a slightly different twist in that they're not having to come up with the entire explanation or mechanism for why this is happening. We've kind of given some of that information to the students ahead of time. Right? And again, much like I showed you with the Guppy activity, right? Also providing students with some relevant information so that they have some of that content and background that's going to really help them explain what's going on and what's happening in terms of the science related to that investigation. Right.
Okay.
So do we want to?
I was just going to jump in real quick,
Sure.
over here, because we have just a couple of minutes to allow some folks if they wanted to ask some questions. But one of the questions that I think that is related to the work that we're doing here at Bethune-Cookman University is determining the gaps between what the students know and what they should be able to know. And the question is, how do we go about doing that? Of course, that is part of our investigation. But what would you suggest that we quickly we use to begin to narrow down that gap, or at least identify the gap?
So you're asking me how you would identify that gap? Was that the question?
Yeah.
So yeah, I think really one of the best ways to do that, and it's a phrase that I use often, is just ripping the Band-Aid off. So just have the students actually engage in this process. So it doesn't necessarily require any front loading of this is how you argue, this is what an argument is. Just engaging them in an activity, along the lines of what I've showed here today, is a great way to just get started and see what the students do and what they come up with. arguing, as I mentioned, the Coke versus Pepsi thing. Students argue about the best sports team in their local area, or the best college team or something like that. So students argue about things often. This idea of making a statement and backing it up with some sort of evidence, whether it's scientific or not, is a common thing that they do. So seeing how that takes shape in the science classroom is probably the best way to start. And then you can kind of figure out where we need to address or fill in some holes, or add some different resources or something like that.
Okay. Excellent. So any other questions from the audience? Anybody has a question, we can unmute and you can go ahead and
Yeah, yes, we do have one more question. Dorothy Silverman typed in. If you would like to raise your hand and ask in person, that's fine, but also I can also read this out loud from Dorothy Silverman. Is ADI commonly integrated with standard textbook homework or no? What other techniques is it nicely integrated with?
That's a good question. So as far as homework goes within the model, right, you can have students do some of the writing for homework, or maybe generating some of the arguments as homework and that sort of thing. But ADI is really just a model, an instructional model or approach for doing laboratory investigations. So this is not something that you would be doing every day during a typical school year or a semester or something like that. This would be reserved for the lab investigation, and then other times during your curriculum, you would do other instructional approaches that you would more typically do. So, other kind of activities students could do at their desk, or in small groups, or even other lab investigations that take a little bit less time. And to the extent that you involve homework and those activities, that's whatever works for you and your students. But I don't have a particular stance necessarily with regard to homework and ADI.
Okay. Well, we're about 2 minutes past the top of the hour, and I just want to extend a huge thanks to you, Dr. Grooms. I'm sorry if I'm cutting you off.
That's
Actually,
I just wanted to jump to this so folks can see this in the background. There's contact information. There's some resources available. So by all means, reach out, and I'm happy to continue the conversation, through email or other venues, whatever works for individuals.
Yeah.
Great. Thank you.